Hello again. We are looking at question number 32. This is a 1-mark numerical answer type question from atomic and condensed matter physics. It tests your ability to apply Hund's rules to find the ground state of magnetic ion. The answer here is a specific integer, and arriving there requires careful counting of quantum numbers. So the question basically asks for the effective magnetic moment in units of Bohr magneton for the ground state of an ideal isolated 4f ion. The ion has 6 unpaired electrons in 4f shell, 6 unpaired electrons. We need to supply the answer as an integer, so it is asked in integer. So the crucial phase here is ground state. This means we must strictly follow Hund's rules to determine the total angular momentum J. Once we have J, we can calculate the magnetic moment, as you know. So to solve this, we use the Hund's 3 rules. So we solve these using 3 of the Hund's rules. First, we maximize the total spin. S. Second, we maximize the total orbital angular momentum. L. And third, and most importantly for this particular problem, we calculate the total angular momentum J based on how full the shell is. If the shell is less than half full, J is L minus S. If it is more than half full, the J is L plus S. And finally, the magnetic moment depends on J. So this magnetic moment depends on J, and if J turns out to be 0, the magnetic moment would be 0, but we will see it soon. So let us visualize the 4f shell first. Since L is equal to 3, so we have 7 orbitals, because it is nothing but twice L plus 1, 6 plus 1, 7. The magnetic quantum number, that is ml, it ranges from minus L to plus L. So it is minus 3 to plus 3, or vice versa. So these are plus 3, plus 2, plus 1, 0, minus 1, minus 2, and minus 3. So for F shell, we can have so we can place 6 up arrows in the 4, 5, 6 boxes. So the problem states we have 6 unpaired electrons. That's why I added 6 upspin states here. And in the F shell, this corresponds to the configuration 4f6. So the configuration is simply 4f6. We place 1 electron in each of the first 6 orbitals to maximize the spin. So box 7 is empty here, which is ml minus 3. So ml values are plus 3 here to minus 3. In between values are given here. So the total spin, which is 6 times half. So the total spin, which is 6 times half, is simply 3. And the total orbital angular momentum sum is basically the sum of the ml values which are occupied. So that is 3 plus 2 plus 0 minus 1 minus 2. The positive and negative 1s and 2s cancels out. So we are basically left with L is equal to 3. Now for the third rule, that is the shell holds a maximum of 14 electrons. So we have 7 boxes, 14 electrons. Our occupancy is 6. So the half capacity is 6. Currently our occupancy is 6. Since 6 is less than the half filled value of 7, we use the subtraction rule, that is J is L minus S. So we found L is equal to 3 and S is equal to 3. So we have finally our J as 0. And we saw that since the total angular momentum of the ground state is 0, J is 0, the effective magnetic moment, which is proportional to square root of J times J plus 1 must always be 0. So we should note that this particular configuration corresponds to European plus 3 ion, EU 3 plus ion. While it has interesting magnetic properties at room temperature due to excited states, its ground state moment is strictly 0, as we just saw. Here is a key takeaway for this particular problem. In physics exams, always watch out for the 4f6 case, that is europium. It is famous because the L and S perfectly cancels each out in a ground state, leading to non-magnetic result. If you see 4f6, the answer for the ground state moment is 0. A similar example if you saw for gadolinium 3 plus, the J is 3.5, so it is a pure spin moment. So for more examples on calculating magnetic moments, check out the atomic and molecular physics course by Professor Das. That's it for question number 32, and see you in the next one.